Hello and welcome to module 4 for online NPTEL certification course on aero engine gas turbine cycles. So, in last week we were discussing about say turbojet engine. We started discussing about single spool turbojet engine. We have also introduced two spool turbojet engine. We have done cycle analysis for both single spool and two spool configuration in operative of afterburner. Then we have done the discussion based on effect of various cycle parameters on the performance of the engine for both say ground condition as well as cruise condition, or we can say flight condition, and we have solved the numericals also. I am sure with these fundamentals you must be able to do now calculation what we say in terms of cycle analysis and performance prediction. Now, what all we were discussing in week 3, that is say some special kind of engines. Now, in this week we will be discussing about the introduction of a new parameter or say new component in two spool configuration or single spool configuration of turbojet engine, and that is what is say afterburner. So, we will be discussing about what we mean by afterburner, construction of afterburner, what are the need of this afterburner, and then we will be discussing about the cycle analysis for the two spool configuration with operative of afterburner, both for the ground condition and the flying condition, different flying speeds, and we will be discussing about say various cycle parameters on the performance of this engine, both for say design condition or the ground condition and the cruise condition, and we will be solving the numerical. That is what will be building the confidence for you. Now, let us begin with this part. Now, what all we know, this is our single spool turbojet engine, and this is the simplest engine, we can say gas turbine engine. That is what is being used for say aero application or say aircraft application, where we are having compressor, diffuser, combustion chamber, turbine, tailpipe and the nozzle, and we have realized what all are the requirements of these components. Later on we have introduced say new configuration, that is what is two spool turbojet engine. We have discussed what is the reason or what are the reasons why we are going with the two spool turbojet engine configuration. So, if we will be discussing one by one, the major interest is in terms of generation of the thrust with the special application. So, as we are discussing say before or during Second World War, people they are more interested in flying high at high speed, but the purpose was for say fighter aircrafts. Later on they realized they will be using this for the transportation purpose, where they are looking for say more weight to carry, and that is the reason why the thrust requirement will be increased. With the increase of the thrust requirement, we have realized we can improve this thrust requirement by increasing the pressure ratio, turbine entry temperature, and that is what has given the new indication to add more number of components. Suppose say we will be going with the single spool configuration, I will be going with say more number of compressor stages, we will be having more number of turbine stages, and that is what will lead to increase the weight of the engine, that will be increasing the drag of the engine. And in place of having this longer engine, if we will be going with the two spool configuration, our number of stages required will be reduced, because we are taking the benefit as per our Euler's equation. We will be rotating our spools at high speed and low speed. Why we are rotating for the low speed? That is what we have discussed in terms of our limitations with the shock formation. Why we are moving with the high speed? That also we have discussed in order to reduce the number of stages. So, these all things I am sure you are aware of. Now, you are confident about what all we are talking about the single spool configuration and two spool configuration. So, here in this case, this is what is representing my say TS diagram for the single spool turbojet engine. Here this is what is representing say two spool turbojet engine. So, this is already known to you from the last week discussion. Now let's move towards the next. We have realized, say during 30s, 40s, where we are taking say Vittel engine, that's what was a reference, where my turbine entry temperature that's lower. Over the year we have grown up in terms of rise of turbine entry temperature. So we are presently in the range say around 200 2000 K. Okay, now new engines in future that will be having temperature in the range of 2200 K. Now the reason for increasing the turbine entry temperature for say turbojet engine, what we have discussed, that's what is known to you. We have discussed when we are increasing our turbine entry temperature, we will be having the rise of say enthalpy from H4 minus H5 to 4 dash minus 4 5 dash. Okay, that's what will be lead to increase the exit velocity, and that's what will be increasing my thrust. So you can say in order to increase the thrust, we need to go with the higher turbine entry temperature. Okay, so you can say if I am looking for higher thrust, then let me go with the higher temperature. But we have realized the problem is with say turbine entry temperature. The turbine entry temperature, that's what is a metallurgical constraint. If we move beyond certain temperature, the blades of the turbine will get melt. Now suppose if I consider, say I don't want to move with the rise of say turbine entry temperature, but I have special kind of requirements now. Say what are my requirement? I say I want to temporarily increase the thrust for the short duration. Suppose if I consider say short takeoff or heavy takeoff in hot days, we have discussed about this in week 1. Rapid climb, if I am looking for, I want to go with the acceleration from subsonic to supersonic speed. Now being application for say military purpose, we are also looking for combat maneuvers with the higher value of G. Now these are the requirements for say my engine. Now how do we address this? How do we gain this thrust? Okay, suppose say my engine is same, I don't want to increase or I don't want to add more number of rotating components. I am having constraint with the temperature. I don't want to increase the size of the engine, but still I am looking for all these requirements. How do we address? So this is what it says, like I am looking for the thrust augmentation. That means I want to increase the thrust. It says, suppose say I want to increase the thrust of the engine beyond my design value. How do we do it? Very first, as we have discussed, it says you increase your turbine entry temperature. If you are increasing the turbine entry temperature, it says we are able to increase the thrust per unit engine mass flow rate, or we can say by increase of specific thrust. We can increase the net thrust for the same size because we are only changing the turbine entry temperature. And here we are having red light, red indication, that is in terms of metallurgical limitations and centrifugal stress in the turbine rotor. So that's what is putting the constraint to us in terms of increasing the turbine entry temperature. Now from the thrust equation, if we look at, this is what is addressing my exit velocity V9. There is one more possibility we have. The possibility it is to increase the engine mass flow rate. If I say I am increasing the mass flow rate, that will be increasing my thrust. So if you recall, we were discussing the performance parameter in terms of change of mass flow rate. This is what we have found. But at the same time, what is happening is with the increase of my engine mass flow rate, it will be increasing the size of the engine, and hence my drag and weight of the engine will be increasing. So these are the limitations. Now the situation is I don't want to change my engine. My engine size I want to maintain same, but I want to improve the thrust. And in order to address this, people they have done lot of research and developments, and it says there are possibilities. One, it is by water injection, and second, that's what is by reheating or afterburning. So, in first week when we were discussing about say engine thrust, that time we have discussed about the ingestion of water. That is what we will not be discussing in detail for this week. Our major focus here is reheat or afterburning. So, let us try to understand what is the meaning of this afterburning. Okay. Now, suppose if I consider this is my 2-spool turbojet engine. For this 2-spool turbojet engine, this is representing my ideal cycle, and here if you look at, this is the indication of my ideal velocity or ideal exit velocity V9. Now, what I want to do, I want to improve the thrust, I want to augment my thrust. How can we do it? So, here it says I want to augment my thrust, I am looking for my exit velocity to be in this range. Now, what it says, if I will be having my turbine work, that is what is here, if I will be adding, it says I need to increase my turbine entry temperature from this point to this point. So, it says by incorporating the higher turbine entry temperature, we are able to improve the exit velocity, and by mean we are able to improve the thrust of the engine. Now, here in this case, as we have discussed, we cannot move beyond certain turbine entry temperature because of our metallurgical constraint as well as my centrifugal forces which are happening in my turbine rotors. So, do we have any other alternative? Can you try to find the solution for that? What can be done? Here in this plot only, that has given some clue to you. Okay. Let us see how you are thinking of. Suppose say I will be doing something, it says I will be adding my heat along my this line, constant pressure line, that is what will be increasing my velocity at the exit. Can we do it? So, let us try to look at. So, here in this case it says this is my 2-spool turbojet engine with afterburner. Just look at the difference in terms of the construction. What is the case? The exit coming out from my LP turbine, that is going to tailpipe, and that is what will be connected with the nozzle for inoperative of my afterburner. Here in this case we are having say afterburner that will be placed after my LP turbine. Then we will be having our tailpipe, and this is my nozzle. So, construction different you can see here. Now, basically I am incorporating my afterburner. So, just realize one thing, the terminology. So, here if I consider this as my burner, say I am putting my one more burner after main burner, and that is the reason why we can say that as afterburner, isn't it? Okay. So, now here in this case we are having 2 combustion chambers, 2 burners. First here it is main burner or main combustion chamber, second burner, that is what is my afterburner. Okay. Now, let us try to look at what is a change on my TS diagram. So, this is what I say in terms of our actual condition. It says here this is what is my exit velocity if I consider I am not having afterburner in operation. Now, what do we do? Here as we have discussed, we will try to add the heat at constant pressure. So, let me put the heat at constant pressure. So, here this is representing constant pressure heat addition which is happening in my afterburner, and I will be able to raise the temperature to say 7 or 8. And here if you look at, this was my enthalpy, that's what was representing my exit velocity, and here this is what is my enthalpy difference, that's what is representing my exit velocity. Now just look at what we have done basically. By providing the additional amount of burner, we are able to raise the temperature. Now you will say, sir, here this temperature why we are increasing, why not this T4? As we have discussed, if I will be increasing my T4, I have limitations in terms of my turbine entry temperature with the metallurgy or material of my turbine. Here in this case what we are doing, the exhaust which is coming out from my turbine, that's what we are injecting here, and I am not having any further rotating components here. That means I can raise as much temperature as possible, and that's how we are augmenting our thrust. So this is representing two-spool turbojet engine with afterburner. The same logic can be applicable for the single spool configuration also. So there are many engines which are single spool turbojet engine with afterburner. Here this is what is two spool turbojet engine with afterburner. So do not get confused saying like single spool may not be having afterburner. With the constraint, with the time, we will not be discussing the single spool configuration. You can understand the logic, that's what will remain same. Now let us try to understand what all components we have. So here in this case, as we have discussed, this is representing two spool turbojet engine without afterburner, and this is what is with the afterburner. Now this afterburner, that's what is required, the proper mixing of fuel and air. Okay. Now let us try to understand. We say we want to add the heat here. We want to add the heat at constant pressure. Now the question is, in order to do this combustion, what is our requirement? Our requirement is oxygen and the fuel addition. Now what is happening? My flow which will be coming out from the turbine, that will be having higher temperature, and those exhaust product that will be having certain amount of oxygen present in that. So what we will be doing? We will be injecting our fuel at some location, and when we are injecting this fuel, by using this burning, we will be able to increase the temperature, we will be able to add the energy. So say like additional amount of fuel burn, that will raise the temperature as much as possible. And here in this case, as we have discussed, we are not having any limitations in terms of thermal aspects, because it is not having any limitation in terms of mechanical stresses also, because this, if you look at, it is nothing but it's a duct, it's a pipe. Okay. Now here what is happening, because of addition amount heat, we need to have the area at the exit to be varied, because it need to handle the large mass flow rate. Under that condition, we are looking for variable area nozzle. So here in this case, if we look at, we are not using variable area nozzle, but here in this case, in order to handle the large mass flow rate, we are looking for variable area nozzle. Now let us look at how the construction is. So this is what is the indicator of say afterburner. Here in this case, the flow which is coming out from the turbine, it will be having higher velocity. That velocity will be in the range of 200 to 400 meter per second. The exhaust velocity coming out from the turbine, that will be in the range of 200 to 400 meter per second. At that velocity, the combustion, that will be very difficult, we know that logic, and that is the reason why we need to decelerate the flow, and for the deceleration of the flow, we are looking for the diffusing passage. So we are adding diffuser. Now this is what will be decelerating the flow. Here in this case, if we look at, this is what is representing my flame stabilizer or the flame holder. They are the aerodynamic devices which will be controlling the flow that is coming out from the combustor. Somewhere here we will be having the spray of the fuel that will be happening. Okay, and here somewhere we will be having igniter. That is what is required for the ignition of the fuel and air mixture. Now downside, if you look at, this is what is a long duct, that is what is called say afterburner duct. In order to have the proper mixing and burning to happen, this duct length requirement will be large. And downside here, if you look at, this is representing say when we are having say non afterburning operation, we will be having our nozzle to be in this position. When my afterburner is off on, that time we will be having this kind of position. That means we are looking for variable area nozzle. So let us look at the construction here. This is what is say afterburner for G85 engine. Here this is what is representing my frame holder. Somewhere here, if we have, if you look at, this is what is my spray bar where the fuel will be injected. Somewhere here, if we look at, we are having torch igniter, that is what will be having say spark plug that will be igniting the fuel and air mixture. Downside here, if you look at, we are having the corrugated surface, they are known as afterburner liner. Since my temperature will be very high, and that is the reason why it required the kind of cooling, and that is the reason why the specific shape, that is what is been given with, and this is representing my afterburner nozzle. Similarly here, this is a Tumaski R29 engine, that is what is fitted with say MiG-23, and this is representing the cut section in order to understand in say actual sense. So here if you look at, this is what is representing my frame holder. Now this frame holder what we have, that will be subjected to say expansion and contraction, that will be taken care of by providing the special kind of mechanism here. So here if you look at, this is representing my spray bar, torch igniter, say flame holder, afterburner lining, and here if you look at, this is representing my afterburner nozzle linkages. More close, you can go with this YouTube video that will be giving you more detailed understanding of say afterburner. Now the question is, now when I am incorporating this afterburner, what will happen with my efficiency, what will happen with my specific fuel consumption. So let us try to look at the case. So here if you look at, this is indicating my say cycle. Here in this cycle, this is what is without afterburner. So if you look at, if I will be putting this line is a A34B, that is what is representing the amount of heat what we are supplying, and here below this 2D, that is what is representing the amount of heat, that is what will be rejected with, and this is representing my work done. Okay. Now here in this case, when I am incorporating my afterburner, the amount of heat supply, that is what will be given by area under the curve B, 6, 7 and C. And if I will be putting say amount of heat rejected, then this is what is representing the amount of heat rejection, and this is what is my additional work done because of my reheating, or when we say we are having afterburner. Okay. So here we can say this is what is representing my useful work, and this is what is representing my useful work. Now the question is, say we must realize this combustion is not happening at high temperature. Okay. This temperature is not higher, and that is the reason why my combustion efficiency will be lower, and that is the reason why we will be having my specific fuel consumption to be higher, but it is not the reason why we are having specific fuel consumption to be higher. So let us try to realize, if we will say my specific fuel consumption under dry condition, that will be given by my work done or maybe thrust divided by MF. When we will be having afterburner, that will be given by thrust divided by this MF afterburner minus MF dry, and this is what is representing my overall specific fuel consumption. So, we can say by incorporating this afterburner, basically we are increasing our specific fuel consumption. Now, what is happening with the efficiency? Let us try to look at this part. So, here this is what we have discussed. If you observe here, see this cycle analysis, when we are doing that, cycle has lot of informations, but if you will not be able to analyze this in a proper way, then that will give you misleading information. So, here in this case, let us try to compare, say this is the point where my fuel is getting injected in my core engine or main combustion chamber, and here if you look at, this is the temperature at which my fuel is injected in afterburner. Now, here in this case, both the cases my pressure, that is what is different. Okay. Let us try to look at what is happening. Here my P3, that is what is higher than that of my P5, because this line, if I will be extending, it says these lines are diverging line. So, my combustion in afterburner, that is what is happening at lower pressure. Okay. So, here if we compare, this is what is the indication. What it says, my thermal efficiency of the reheat system, it is worse than the thermal efficiency of my dry engine. Here the major reason is what we have, my P6, the pressure at which my combustion is happening in afterburner, which is much lower than that of my P3. Okay. So, try to analyze, try to realize this part. This is what is very important. Now, let us try to understand what we say in terms of, say, thrust specific fuel consumption. So, what we will be doing? We will take the plot for, say, pressure ratio versus specific fuel consumption. This specific fuel consumption we have kept in terms of dry specific fuel consumption, then reheat specific fuel consumption. This is representing my overall specific fuel consumption, and we are having P6 by P atmosphere, because this pressure, that is what is very important. So, if we look at this plot carefully, it says with increase of my pressure ratio, specific fuel consumption, that is what will be reducing for, say, my dry condition. In line to that, when we are increasing our pressure ratio for the reheat operation, our specific fuel consumption will be more than that of my specific fuel consumption for the dry condition, and here somewhere we will be having overall specific fuel consumption, what we have discussed in the last slide. Now, what is happening with my P6 by P atmosphere? What it says, when I am increasing my pressure ratio, my P6, this pressure value, that is what is increasing. So, here if you look at my P6 by P atmosphere, that is what will be increasing, and if you will try to observe carefully, I will be having the optimum value of specific fuel consumption, that is what is happening at, say, higher P6 by P atmospheric pressure. Okay. And we can say this is what is my optimum pressure ratio now. Okay. This is what is my optimum pressure ratio. Now, let us try to analyze this in terms of what is our requirement. It says we are plotting specific thrust versus specific fuel consumption, and here if you look at the full line, that is what is representing my pressure ratio of 20, dotted line, that is what is representing my pressure ratio of 30, and this is representing my turbine entry temperature. So, what we have realized, we can say here, if I am increasing my pressure ratio and if I am increasing my turbine entry temperature, I will be having reduction of specific fuel consumption. Suppose if I consider I am having my turbine entry temperature 2100 K, we can realize for the high pressure ratio, my specific fuel consumption, that will be reducing. Now, here in this case, this is what is representing when we are having our, say, afterburner temperature, this temperature T7 to be 2100 K. Now, suppose, say, if I will be increasing my turbine entry, say, this afterburner temperature, we will be having the reduction of specific fuel consumption. Okay. Now there is a particular value of P6 by P atmosphere where we will be having say specific value or optimum value of specific fuel consumption. So we must realize here what we have discussed in last week, last numerical, where we were discussing about say increase of pressure ratio, we were discussing about the increase of turbine entry temperature. Now just try to correlate that here, and here we are incorporating our afterburner. So you must realize two spool turbojet engine without afterburner, it is having some performance. Now two spool turbojet engine with afterburner will be having different kind of flavor. Okay. Now here if we look at, the question will come, what is the reason why we are having say afterburner or why we want to add the afterburner? It says by incorporation of the afterburner we will be able to increase the jet velocity. When we are increasing the jet velocity, we can say our thrust that will be increasing, and this we will be able to do with addition of not much addition of weight or the complexity to the engine. Secondly, it says there is a special requirement of temporary increase of the thrust for the short duration. Suppose if I consider takeoff, climb, acceleration or combat maneuvers, under that condition we want to increase the thrust for the short duration and we are not changing our engine. Okay. So that requirement can be fulfilled here. There are special application for the military jet. So here in this case, if you look at, suppose say for naval application where my takeoff length, that's what is short. Okay. Now under that condition, within short duration with the short distance available, if we will be operating the afterburner, we will be able to achieve the altitude with short distance and short time. That's what is a major requirement. It is also been helpful for the high speed maneuvers in dogfight configuration. Okay. So we can say my afterburner requirement, it has a special application towards the military purpose. Okay. But still, suppose if I will be talking about the Concorde, for that Concorde we were having this engine, Olympus engine, that's what is not been used for the military purpose, that the purpose of incorporation of the afterburner is different. That's what is to achieve higher flying speed. Okay. Now what all will be the challenges in terms of afterburner? So if we look at carefully, it says when we are all incorporating the afterburner, then my nozzle that need to be adjustable nozzle, because we will be having operation of afterburner for the short duration. Most of the time that will be unoperational afterburner. So under that condition we need to have our nozzle to be variable firstly. Second, it says it required lot of fuel in order to generate the power, and that's the reason why we are not using afterburner for the long duration. Suppose if you consider say if I will be operating my afterburner, it will be consuming gallons of my aviation fuel within fraction of seconds, and that's what will be very challenging, and that's the reason why we are not using this kind of configuration for our commercial airlines. They are mainly being used for the military purpose. Okay. Now since my engine will remain same, and that's what will be fitted with the afterburner and afterburner tailpipe and my nozzle, and that's the reason why when my engine is operating under dry condition or the unoperational of the afterburner, that is putting additional weight to my engine. Okay, and that's the reason why we will be having loss of thrust. Okay. Now in overall sense, if we look at my weight, power plant that will be increasing because of heavier pipeline and afterburner equipment. So lot of research and development activities which are been going on in terms of designing these afterburners, design of afterburner liners, cooling mechanism, design of the exhaust nozzle for the special requirement. So, here for this fundamental course, this information what all we are discussing about the afterburner, that is sufficient, and here we are stopping with this session. I am sure now you are having much more maturity and understanding in terms of what we say as afterburner or the reheater. Okay. Now, you will be able to understand what is the reason why we are incorporating the afterburner, what all are the benefits of incorporating this afterburner, and what are the limitations of this afterburner. With this all fundamentals, here we are stopping with. Thank you. Thank you very much for your kind attention. In next session, we will be discussing about, say, how do we go with the cycle analysis by incorporating this afterburner. Thank you. Thank you very much.